Good morning, everybody. Today we will continue with chapter 23, electric potential. What we have is in this chapter, we will learn electric potential energy. During the physics 1, during the last semester, we have learned potential energy. Okay, we have learned many information related to the potential energy, and we have discussed many different situations related to the potential energy. And today, we will discuss the electric potential energy of a collection of charges. So you have 2 charges, 3 charges, or many charges. So what is the total electric potential energy of a collection of these charges? Then we will talk about electric potential. So electric potential energy and electric potential are different terms, okay? And they have different physical meanings. We will go into detail. And we will learn how to calculate the electric potential that a collection of charges produces at a point in space. What is the meaning of this? So let's consider here we have a positive charge, and here at P point in space, you would like to calculate the electric potential. Remember the Coulomb's law, remember the Gauss law. During last 2 weeks, we have discussed how to calculate electric field at P point in space due to the positive charge or negative charge here, okay? So today, we will learn how to calculate the electric potential that a collection of charges produces at a point in space. So we have electric potential energy. The symbol is U, as we have used in the first semester in physics 1, and we will learn electric potential. This is shown with V, capital V, okay? Then in the next lecture, we will learn how to use equipotential surfaces to visualize how the electric potential varies in space. So remember the electric field produced by this charge. So in space, the electric field here in this P point on the right side, or here in S point on the left side, electric field changes depending on the distance between the point in the space and this charge here or source here. Electric potential also has more or less the same mechanism. Depending on the position in the space, electric potential changes, and we will use equipotential surfaces to visualize the electric potential variations in space. And finally, we will use electric potential to calculate electric field. So just consider that electric potential is given, and then how to calculate electric field by using this electric potential. Or electric field is given, and how to calculate electric potential by using this electric field. So we will also learn this relation between electric potential and electric field. And what else? We will also learn work, okay? So remember the work from the physics 1 again. Work is given with negative delta U, the negative sign of the change in the potential energy, okay? Or it is also given with this expression, the change in the kinetic energy. Remember this information from the physics 1, okay? And we have also learned that in case of energy conservation, I can also write this expression U1 plus K1 is equal to U2 plus K2, okay? So these are the old information from the physics 1, and in physics 2, in this chapter and also in the forthcoming chapters, we will use this old information, and it will be very useful for us. So this is the summary of this chapter. Then let me continue. Here you see a welding process. In one type of welding, electric charge flows between the welding tool and the metal pieces that are to be joined. So here you have a welding wire, okay, and here you have a metal, and there's a joint here, and you would like to connect this joint by using welding, and you use a chassis here, okay? So there's a contact in between, and with the electric charge flow between the welding tool and the metal pieces, then we can connect two parts of the metals. So the tool must be held close to the metal pieces in order to maximize the electric field, because electric field depends on the distance. So I am meaning this one here. You have a welding tool, and here we have two metals, and you would like to connect them by using welding, okay? And here you see a potential difference between this welding tool and this metal piece. And then, due to the potential difference, a glowing arc fuses the pieces together. So there's a glowing arc here. So you produce charge transfer, or you produce electric charge flow, okay, between this tool and this metal. So then during this flowing, metal is reached to the high temperatures, and then two metal pieces are joined together. So this is very common example of electric potential. There are also many other industrial and daily applications of electric potential. There are also many biological examples. Today I will also talk about this. So in summary, electric potential energy or electric potential is an integral part of our technological society. Okay, very important topic for our daily life. Now let me continue with the electric potential energy in a uniform field. During the chapter 21 and also in chapter 22, we have discussed special conditions for uniform electric field. Okay, so what is the meaning of uniform electric field? Let me repeat this part again, and then I will continue. So this term is very important, uniform electric field. And what is the electric potential energy in uniform electric field? Let's consider, here we have a positively charged metal plate, and here we have negatively charged metal plate. Then in between we have electric field, right, from positive to the negative. But what is the meaning of uniform field? Uniform field means that between these two plates here in this region, everywhere the magnitude of the electric field and also the direction of the electric field are same. Okay, so here we have same electric field, here we have same electric field, here we have same electric field. Okay, this is a uniform electric field. So let me start with this explanation. Then let's continue to discuss the electric potential energy in a uniform electric field. Here again we have positively charged plate, and here we have negatively charged plate. Okay, and the distance between the plates is given with d. Here we have a point on the surface of the upper plate, and here we have B point on the surface of the bottom plate. And here we have a point charge Q0 here, somewhere here, and it has charge of Q0, and it is moving in a uniform electric field. It is positively charged, and for this reason the force due to the electric field will be downward along the electric field. Okay, this is the direction of the electric field here, and also the force due to the electric field will be downward because here we have a positive charge. Okay. So then by using this electric field, by using this electric force, we can move this charge from A point to the B point. Okay. So, and you can use this path, or you can use this path, or let me choose another pen. For example, you can use this path. Okay, you are moving this charge from A point to the B point by using different ways, different paths. Okay, so what about the work done by this force, this electric force? Okay, why we have a work here? Because here I have a force and here I have a displacement between the plates. And if we have a force and if we have a displacement, then we can talk about the work. We have discussed all these things in Physics 1. Okay, I will not go into detail. I will just use our previous information. But if any explanation is required, I will go into detail. Don't worry about it, okay? Now, let me remind you this statement. You will also remember such information from Physics 1. As the charge moves downward from point A to point B, the work done by the field is independent of the path the particle takes. What is the meaning of this? Maybe you already remembered from the Physics 1. So this is the initial point of the particle A, and this is the final position of the particle B, okay? So this positively charged particle is moving in a uniform electric field. Then, due to the electric force, there is a work, okay? And what about the magnitude of the work if I follow this path on the left side, let's say W1, and what happens if I follow this path, and what about the work along this path, and what happens if this charge directly moves from A to B by using this path, then what about their magnitudes? During Physics 1, we have learned that it is independent of the path, okay? So here we have the same force in each cases, okay? So the force is same and the total displacement between A and B also same for all conditions. Then the work for all passes is same, okay, and it is equal to F times D. Then let me continue. So the work done by the electric field or the work done by the electric force is given with this expression. The work done by the field to move the point charge from A point to B point is given with this integral from A to B. This is the force. This is the dl, displacement. You remember this formula, this information from Physics 1. And you see this is scalar. Then I can also write this expression in this form, F cosine phi dl. This is the work done by a force. Okay. Then here in this case, on the right side, we have a situation. Then for this case, the work is given with F times D. And what is F? F is given with Q0 times E. Okay, just put it there. Then finally, we have this work. As I have explained at the beginning of my lecture, work is also given with delta U. Okay, we have also learned this information in Physics 1, the change in the potential energy of the particle. Okay, so this is the potential energy of the charge at A point, and this is the potential energy of the charge at final point. Okay, and I can also write this one in this form, or I can write this one as a negative of change in potential energy minus delta U. Okay, this is work definition. So I can write work like this. I can write work like this. And I can also write work in this form. I have also given this information at the beginning of this lecture. So remember the work energy theorem from the physics 1. It says that the change in kinetic energy, delta K, final energy of the charge at B point minus initial energy of the charge at A point. So this is the change in the kinetic energy during a displacement equals the total work done on the particle. So the work AB can also be written in this form, delta K. It can be written in this form as we have done, minus delta U, or it can be written in this form, F times D or Q0 ED, okay? I can write this work in these three forms. So you will get this one. This is the work energy theorem, which we have learned during the last semester, okay? Initial kinetic energy of the charge plus initial potential energy of the charge is equal to final kinetic energy of the charge plus final potential energy of the charge. Okay, I hope this part is clear. We have discussed three different forms of the work, okay, done by the electric force during the displacement of this charge under electric field and electric force due to the electric field. Do you have any question here? Then let me continue. I can write work in this form as we have discussed, minus delta U. This is negative sign, final potential energy of the particle minus initial potential energy of the particle. And I can also write this UB like this. This is the final potential energy. Okay, Q0 E YB. What is the YB? YB is this one. This is the B point here. And just consider that the particle is here at the beginning and it is moving in this direction under the electric field. This is the A point, this is the B point, and this is the distance YA, and this is the distance YB, okay? And the potential energy here is given with UB, and the potential energy here at the beginning is given with UA. I have just opened this potential energies here, okay? Nothing is new for you. So then instead of this expression, I can write this one. Then what is this? YA minus YB. What is this? This is total displacement. You can say X or you can say D, okay? Then this is the potential energy written with Q0 EY. Okay, so actually the title of the lecture is electric potential energy and electric potential, okay? Now we are defining the electric potential energy and then we will continue with the electric potential. Now let's discuss different conditions. If we have a positive charge moving in a uniform field, here again we have positively charged plate, and here we have negatively charged plate at the bottom, and we have a uniform electric field in between. Then here I have a positive charge, and due to the electric field there is the electric force acting on this positive charge. So what about the direction of the force? The force direction will be along the electric field direction because here we have positive charge. Or you can also understand from this condition, Here I have positive charges on the metal plate, and this point charge is also positively charged. Then there will be repulsive force. And here I have negative charges on this side of the plate. Then these negative charges will attract this positive charge. Okay, then this particle will move from the positive side to the negative side due to the electric field. And at B point, this is the distance to the origin here. And at A point, this is the distance to the origin, YA, as I have shown you here in this equation. And what about the work and potential energy here? Be careful here. It is very easy. It is not necessary to keep any formula in your mind. If you understand the idea behind it, it will be very easy for you. Let me change the pen. Then, what about the work and potential energy? Is work positive or negative? What about the potential energy? Potential energy is increasing or decreasing during the movement of this positive charge from A point to B point. What happens to the potential energy and what is the sign of the work? Work is given with this expression. I have here positive charge, okay? And then I have positive work. You can also understand this one. What about the force? Force is in this direction. What about the displacement? Displacement also in downward direction. So if force and displacement are in the same direction, the work done by the force is positive. Remember from the last semester, okay? So then here we have positive work. What about the potential energy? Potential energy increases or decreases. It is also very easy to understand. What about the potential energy here at A point? UA, Q0, E, Y, A. And what about the potential energy here? B point, Q0, E, Y, B. So YB is smaller than YA, then UB is smaller than UA. Then potential energy decreases, okay? During this movement, potential energy decreases. There is also another physical meaning of this. What about the meaning of potential energy? What about the minimum potential energy? What about the negative potential energy or positive potential energy? Just look at the scale. Let's consider this is the potential energy. This is 0, and this is U, let's say, and this is negative U. So which one is minimum here? The minimum potential energy is this one, and all objects are happy to have minimum potential energy, okay? All particles. So look at the potential energy here. Look at the physics behind it. Here I have positive charges on the plate here. And this is also positively charged. And what about the electrostatic force here? Electrostatic force here is repulsive, okay? This Q charge is not happy to stay here. It would like to move in this direction, okay? Because there is a repulsive force in between. And what about the negative charges here on the surface of this plate and positive charge here? So there will be attractive force in between. Then this positive charge would like to be here, okay? Why? Because potential energy is minimum here. Here, potential energy is maximum. Okay, it does not want to stay there. Energy is maximum there, and it prefers minimum energy. Okay, I hope this part is clear. Then let me continue with the second condition. We have again positive charge, but now it moves opposite the direction of the field. We have positive charge here. This is the initial position A. The charge is positive, but this charge is moving upward direction. How it could be possible? It can possible, okay? In some conditions, by using another forces, you can move this positive charge opposite to the electric field, okay? But now we will discuss what is the behavior of this positive charge under these conditions. So this is the initial condition of the positive charge. This is the final condition of the positive charge. And then it moves from A point to B point. What about the direction of the electric field? From positive to the negative. So direction of the electric field is downward. What about the electrostatic force, electric force due to the electric field? Electric force is also downward, right? So the force due to the electric field would like to move this charge downward, but it is moving in opposite direction. Let's say it has initial velocity, okay, before entering this area, let's say. Then, what about the work? What about the work? Remember the sign of the work. We have force and displacement. The sign of the force is downward, but displacement is upward, okay? Because it is moving from A to B. Then the sign of the work is negative. And what about the potential energy? What about the potential energy? It is increasing or decreasing. Here, actually, this is positively charged, and here we have negative charges on the plate here, and then there will be attractive force and energy will be minimum here, or I can write energy like this, Q0 EYA. And when it is moving from A to B, potential energy at this point, at B point, will be like this. EYB, what do you see here? Potential energy is increasing, okay? Now here at this point, we have more potential energy. What is the meaning of this? More potential energy. This is the U, this is the positive U, this is the zero, this is the negative U. So here we have positive charges on this plate, and this is also positively charged, and there's a repulsive force in between. This charge is not happy here, and it is happy here at this point, close to the negative plate. For this reason, when this positive charge is moving from A to B, potential energy increases, okay? So these are the conditions for the positive charge, work and potential energy. Any question here? Okay, let me continue with the negative charge. I will discuss same things with the negative charge. And again, here we have a charge and we have uniform electric field, but now the charge is negative. Okay, so what about the work? Is it positive or negative? And what about the potential energy? It is increasing or decreasing? Okay, so we have negative charge and it moves in the direction of the field. This is the direction of the electric field, again downward from the positive to the negative. And what about the force acting on this charge? Since this charge is negatively charged, then the force will be opposite to the electric field. Electric field is downward, but the force is upward, since here we have a negative charge. Okay, so this is the direction of the force. What about the displacement? Displacement in the direction of the field. So the charge is moving from A to B point, downward. What about the force direction? Upward. Then the work negative. The field does negative work on the charge. Okay. And what about the potential energy? Let me clean the board and discuss the potential energy. I hope now you understand better because we are discussing the third example. This is the UA, this is the UB. And if you write Q0EYA and Q0EYB. So you can understand that UB is bigger than UA. How it could be possible? Because here we have a negative charge. Okay. You can better understand also in this way. Here we have positive charges. And here we have negative charges. And this negative charge is happy to stay close to the positive charges, and then potential energy is minimum here. But when this negative charge is moving from A to B, here we have negative charges, and this negative charge is not happy to stay with these negative charges. Okay, then potential energy increases during the movement from A to B. Is it clear? Do you have any question? Then let me finish this part with the last example. Again, a negative charge moving in a uniform field. But now the negative charge moves opposite the direction of the field. So here we have positive plate. Here we have negative plate. This negative charge initially at A point, and it moves upward to the B point, opposite to the electric field. Electric field is downward and displacement is upward. Okay. So what about the force due to this electric field acting on this negative charge? So force is given with Q0 times E. So since here we have a negative charge, then the direction of the force will be opposite to the electric field. Electric field is downward, and the force due to the electric field acting on this negative charge will be upward due to this negative charge here. Then what about displacement? Displacement is also upward, then the work is positive. The field does positive work on the charge. Then what about the potential energy? Again, let me clean this part and discuss the potential energy. Look at the potential energy here. UB, Q0E, YB. And look at the potential energy here, UA, Q0E, YA. Okay, so which one is bigger? Of course, this YA is smaller than YB, but here we have negative charge again, don't forget. Okay, so which potential energy is minimum? UB is smaller than UA. In terms of physics, in terms of repulsive and attractive forces between charges, you can also easily understand in this way. Look at this part, negative charge, and negative charges here. There will be repulsive force here, and potential energy will be maximum. Okay, and this negative charge is not happy to stay here because potential energy is huge here. Okay, and if this charge goes to B point, this is negatively charged, and here we have many positive charges, and there are attractive forces between positive charges and negative charge here, then the potential energy will be minimum here. Okay, then the final energy at B point is smaller than the potential energy at the point A. So potential energy decreases. Do you have any question here? Okay, up to this part, we have discussed the potential energy of a point charge. But what about the electric potential energy of 2 point charges? Here, I have a positive charge, Q, and we know that we have electric field lines from the charge to the space in case of positive charge, okay? And somewhere here, we have another charge, test charge, Q0 charge, okay? Then what is the electric potential energy of this Q0 and Q? How to write this one? So now we will learn this. And again, let me remind you that the work done by the electric field of 1 point charge on another does not depend on the path taken. So here we have positive Q charge, and due to this positive charge, this Q has electric field lines from charge to the space, and this electric field applies a force on this Q0 charge, okay? Then, with this force, this Q0 charge moves due to the electric field, and this electric field does a work, okay, on the Q0 charge. So just consider that at the beginning, here we have the Q0 charge. Q0 charge is here at the beginning, at A point. And finally, I would like to carry this Q0 charge to this point, B point. This is the final position. It can follow this path, or it can follow this path, or it can follow another path. What about the work? Work is independent of the path taken. Okay, we have discussed this one. And what about the potential energy between this Q0 charge and this positive Q charge? Here we have distance in between when the Q0 is located at A point. And then what about the potential energy between Q0 when the Q0 is located, this final condition, and what is the potential energy between Q0 and this Q charge? Then in this case, in final case, we have this distance RB, okay? Now we will discuss these things. So what is UA and what is UB if we have two charges? One is Q charge, the other one is Q0 charge. And what is the potential energy at A point and what is the potential energy at B point? Or what is the potential energy of 2 point charges? So the electric potential energy of 2 point charges only depends on the distance between the charges. You can write potential energy between these two charges when the distance is RA, or you can write the potential energy when the Q0 charge is located here B and the distance is RB, okay? Then the electric potential energy of 2 point charges is given with this expression, 1 over 4 pi epsilon 0 epsilon 0 is constant. You have already learned in the first lecture, or you can use K constant here. And this is the Q times Q0 over R. This is the distance between two charges. What about the sign of the potential energy? So potential energy is given with 1 over 4 pi epsilon 0 Q0 over R. So what about the sign? Positive or negative? It depends on the charges. It depends on the sign of the charges, okay? So if Q and Q0 are negative charges, then the sign will be positive. You will be positive, okay? And if Q and Q0 are positive, then again potential energy will be positive because you multiply positive and positive. In this case, you multiply negative and negative. But Q is positive and Q0 is negative. Then what about potential energy? Potential energy is minimum, negative, okay? Again, also for the opposite condition, negative Q charge here and positive Q0 charge here will give us negative potential energy, okay? And now let me discuss the final condition. We have Q charge, and here we have Q0 charge. And the distance in between is huge. Just consider that the distance goes to infinite. And then potential energy is 0 in between because they are far from each other. You can also see this information, this result from this expression, 1 over 4 pi epsilon 0 Q0 over R. If R is huge, goes to infinite, this goes to 0. Okay, so now let's discuss the potential energy. I have already explained here, depending on the sign of the Q, sign of the Q0, the potential energy will be negative or positive, okay? And here we will discuss these situations. I have two positive charges here. This is the Q and this is the Q0. And look at the formula. Positive, positive. U will be positive, right? Here we have distance R between two positive charges. And what happens if this distance increases or decreases? Depending on the increasing and decreasing of the distance between charges, this potential energy changes, okay? If you have big distance, here we have R, and here we have potential energy. If you increase the distance, 1 over R, if you increase the distance, then potential energy decreases, you see? Or if you decrease the distance, potential energy is increasing. And potential energy is always positive. This is the 0, and this is always in the positive side because we have same charges. What is the meaning of the decreasing and increasing of the potential energy? If potential energy is big, then the particles are not happy, okay? So look at the potential energy in between. This is positive, this is 0, and in this range, potential energy is positive. only its magnitude changes by the distance, okay, if we have two positive charges. So what is the meaning of potential energy here at this point, or potential energy at this point? Here, positive charges are close to each other at this point, and here positive charges are far from each other. Okay, so since they are positively charged, there will be repulsive force, and they are not happy to stay close to each other. And if they are far from each other, then potential energy decreases, they are happy. But if you make them close to each other, potential energy increases because they are not happy, okay? Minimum energy is preferable always. So you can also apply the same rules for the two negative charges. If you have negative charge here, then there will be again repulsive force in between, and potential energy will be positive, okay? And we will talk about again the same graph of the potential energy. Do you have any question here? Let me continue with another situation. Here we have two charges, Q, Q0. One is positive, the other one is negative. Then U is negative because there is an attractive force in between, okay? So energy is negative, close to the minimum. And another opposite situation, again, the potential energy is negative, okay? So what do you see here? This is the zero, and this is the potential energy. And here in this range, potential energy is always negative, okay? And what happens if you increase the R here in the equation? 4 pi epsilon 0 Q, Q0 R. If you increase the R, what will happen to the magnitude of the potential energy? It will decrease in magnitude. And if you decrease the R, then potential energy will increase in magnitude. But here we have negative U, negative potential energy. If this R is very small, then I have here huge negative U. But since this is negative, this is very minimum energy. So if these two charges are close to each other, then R is smaller, then the magnitude of U is bigger, but due to the negative sign, we have minimum energy here. And then they are happy to stay together because the force between positive and negative charge is attractive. And if you would like to make them far from each other, at this point, for example, you would like to increase the distance between the charges, okay? Then you will have again negative U, but the magnitude of U will be smaller, okay? Actually, which one is minimum? This is the minimum energy. This has more minimum energy than this condition. Okay, you know of this information again from the physics one. I hope all these discussions are clear. If something is not clear, please let me know. Any question? Okay, here I will discuss the potential energy with several point charges, and then I will show you two applications. Here at A point, I have a Q0 charge. This is Q0. And here I have Q1 charge. And here I have Q2 charge. And here I have Q3 charge. These charges can be positive or negative, okay? It doesn't matter. And the magnitude of the charges can be different from each other. And also they can have different distances from the Q0 charge, okay? Then what about the potential energy associated with this Q0, okay? what is the total potential energy of this Q0? The total potential energy of Q0 is written in this form. So what is the potential energy in between? Let's say U1. The potential energy in between U2. Potential energy in between U3. So total electrical potential energy is given with U1 plus U2 plus U3. If you have more charges, then it will go. Okay? And you can write each one with this expression, 1 over 4 pi epsilon 0 Q1 Q0 over R1, okay? And then it goes, then you can collect them in this equation. This is the charge of the particle at a point, and this is constant. And here we have Q1 over R1. And here we have Q2 over R2. Here we have Q3 over R3, okay? Then you can also write this expression in this form. Sum of the charges over distances. Do you have any question in this part? Then let me finish this part with this example. We have discussed electric potential energy, okay? And we have considered that we have uniform electric field. Let's consider this is the positively charged, this is negatively charged, and here we have positive charge, and it is moving under the electric field, uniform electric field produced by these plates. Or here I have positive charge. It has electric field lines from charge to the space, okay? And here we have a Q0 charge. And due to the electric field of this positive charge, this Q0 will feel a force, and I can write a potential energy associated with Q0. Okay, so we have discussed all these things. What about the applications? Here we have a space application. This ion engine for spacecraft uses electric forces to eject a stream of positive xenon ions at speeds in excess of 30 km per second. So what do you see here? This is a thruster. As much as I remember, it is written like this in satellites, in spacecrafts. And here, let's consider we have positively charged xenon ions, okay? So they are ejected from this area to the space, okay? And they have certain mass, and due to the action-reaction mechanism, which we have discussed in Physics 1, this produces a forward thrust to the spacecraft, okay? So this mechanism is used also in satellites, in other spacecrafts. Recently, for example, you remember during the last year, few months ago, SpaceX company sent Crew Dragon. This carried 2 astronauts to the International Space Station in space, okay? And here you see on the right side, there is International Space Station, and on the left side, this is the Crew Dragon, and Crew Dragon is moving slowly through the ISS, okay? And then finally, they are connected, okay? So in space, how to adjust this point, perfect alignment, perfect adjustment between the Crew Dragon and ISS, how to do that? This is done by using this ion engine, okay, these thrusters. If you watch the real video of this connection of Crew Dragon and International Space Station, you will see this one. This is the, let's say, Crew Dragon, and there are some ion engines here in this part. maybe also in these parts. So in order to align, in order to move this Crew Dragon, you eject ions, okay, from these sides. Maybe in also some space movies, you can see this part of things, okay? So you eject ions in this direction and you provide thrust in opposite direction. You eject ions in this direction, you provide opposite thrust in this direction. I hope this is clear, okay? This is the very important application of electric potential energy and electric forces in ion engines. Okay, let's continue with electric potential. Potential is potential energy per unit charge. We have already learned electric potential energy. This is the charge, and this is the potential. Potential energy per unit charge, or you can write this one. Potential energy can be written with Q0 times V. And what about the unit of this potential? Unit of potential is volt, okay? Or you can write it Joule per Coulomb. This is potential energy given with the unit of Joule, and this is the charge, unit is Coulomb. Then you can write the potential with Joule per Coulomb. And now we will learn the relation between work and potential. In the previous part, we have seen the relation between work and potential energy. And now we will learn the relation between work and electric potential. So here we have a battery. This is the A terminal or positive terminal of the battery. This is the negative terminal of the battery, B side. Okay, and between two terminals, the voltage difference, VAB, is 1.5 volts, okay? And let's consider here we have a charge, Q charge, and this is positive side, this is negative side. And I would like to move this Q charge from positive side to the negative side, okay? Then what about the work done by electric force during this movement of charge from A to B? We know that the work done by the electric force, so here I have positive side, negative side, and then I have electric field, okay, in between, and then we have electric force depending on the charge. Then this electric force does work on the charge during movement, okay? So remember again this formula, F times X. F is the electric force due to the electric field between positive and negative terminals, and this is the displacement you can consider, okay? And this can also be written in this form as we have discussed in the first part of this lecture, minus delta U, okay? I can divide both sides with Q0, right? Then just write it like this. Then here we have, instead of delta U, just use UB minus UA. Okay, here we have again Q0. And then what do you see here? Look at this expression. Here I have UB over Q0. Here I have UA over Q0. UB is the electric potential energy at this point, and UA is the electric potential energy at this point, and the particle is moving from A to B, okay, point A to point B, this Q0 charge. And then what do you see here? U over Q0, U over Q0. So I can write this one as VB and this one VA. This is the electric potential of the A point. This is the electric potential of the B point. Okay, UA over Q0 and UB over Q0. Okay, so then just put them here, minus VB minus VA, and then we will have this one. This is the VAB, the potential difference between two terminals of the battery. And this is the work done by the electric force to move the charge, Q0 charge, from A point to the B point, okay? This is the VAB, and it is given with this expression. Just take this one here. You can write this expression. Or the work done on the Q0 charge to move it from A to B is given with Q0 VA minus VB. Okay, they are same equations, and I produced them from this equation. I hope it is clear. So this is the relation between electric potential and work done by the electric force. Okay, so just consider that here we have a Q charge. And here in space we have a P point, and I would like to calculate the electric potential at this P point. Or on the left side I have A point, and I would like to calculate the electric potential in this A point due to this Q charge. Okay, electric potential due to a point charge is given with this expression, 1 over 4 pi epsilon 0 Q over R. Remember the definition of the electric potential. Electric potential is given with U over Q0, right? And remember the formula of the U. U is given with 1 over 4 pi epsilon 0 Q0 over R, right? Then here I have another Q0. This will cancel this one. Then finally we will have this expression. Okay, you don't need to keep new formulas in your mind. You can produce them by yourself because everything is connected to each other. And if we have many charges, just consider here I have Q1 charge, and here I have Q2 charge, and here I have Q3 charge, and I would like to calculate the electric potential here at this A point, VA. Okay, what is the electric potential here at this point due to these 3 charges or many charges? It can be calculated by using this formula. What do you see here? In this case, VA, I'm talking about the electric potential at A point due to 3 Q charges, V1 plus V2 plus V3, okay? If you write each electric potential produced by charges at this A point, then put them here, then you can calculate total electric potential at this A point, okay? So you can write electric potential due to a collection of point charges by using this sum, okay? This is the value of I point charge, and this is the distance from I point charge to where potential is measured. For example, here we have distance from Q1 to the A point, R1, and this is the distance from Q2 to the A point, and this is the distance from Q3 to the A point. Okay, this is the electric potential for a collection of point charges. Okay, And if you have a continuous distribution of charge, what is the meaning of this? During the last lecture and also in chapter 21, we have learned thin, long charge rod or plastic or metal sheet, okay, or spherical shape. We have discussed many shapes. Sheet, a sphere, or ring, okay. We have discussed all of them during the last lectures. And just consider this is charge, this is also charge, this is also charge, this is also charge. So they have certain Q charge and they have continuous distribution of charge. So if it is thin, then the charge density is given with lambda. It is sheet, it has surface charge density. And if it is spherical shape, it has volume charge density. We have discussed all these things during the last lectures. Okay, then in this case, you have to divide the charge into infinitesimal dq elements, okay, as we have done in the last chapters. Then instead of this equation, you can use this equation, 1 over 4 pi epsilon 0 integral dq over dr, okay. R is the distance from charge element to where potential is measured. So here, for example, there is a thin, long rod, and I am choosing a dq element here, okay, and I would like to calculate what is the electric potential here at this VA point due to this rod. And the distance to this A point is given with R, okay, or let's say dr. And if you integrate over all charges, infinitesimal parts in the rod, then you can calculate the electric potential due to a continuous distribution of charge, electric potential due to this rod, electric potential due to this surface, this material, where somewhere here in space or somewhere here in space, okay, anywhere. So this is the electric potential calculation. If you have any questions, please let me know. Do you have any question? Let me continue with the bio application, electrocardiography. So we are discussing the electric potential, V, and just consider here we have A point and here we have B point, okay? So here we have electric potential VA and here we have VB. Just consider that there is no difference between electric potential here and here. Then what is VAB? VAB is 0 if they have same potential. But if VA is different from VB, just like this battery here, we have a potential difference, okay? We have positive terminal here, A, and here we have negative terminal B, and then we have potential difference in between. It is given with 1.5 volt. And this potential difference is also present in our body, okay? In our body, between different regions, there is a potential difference. So here, in electrocardiography, there are several electrodes. Here, you see several electrodes, and each electrode measures potential, electric potential. And then here, let's say A point, B point, C point, D point, E point, F point. And I would like to measure the electric potential in between, VAB. Or I would like to measure electric potential VAC. So in electrocardiography, it is measured, okay? Normally, if this guy is healthy, the potential difference between A and B point or B and D point must be around 1 millivolt, okay? 10 to minus 3 volt between different parts of the patient's skin, okay? But if this is far from this value, you can think that something is wrong. Okay, this can tell you that the electrical activity of the body is not normal. Okay, this produces cardiac. Okay, in Turkish, kalp hastalıkları. So if the voltage difference, electric potential difference between different points of the body is around this value, it is okay. But if it is fluctuates a lot, then there are some abnormalities in the electrical activity of the body. Then you can detect this one by using the electrocardiography. Okay, it is exactly related to the electric potential V. Okay, you are measuring the V and you compare the V for different parts of the body. Now let's continue with defining electric potential from electric field. In chapter 21, we have learned Coulomb's law, and in chapter 22, last chapter, we have learned Gauss' law. So what we have done, we have calculated electric field by using Coulomb's law, and then we have calculated electric field by using Gauss' law. Maybe you have already forgotten the formulas, but let me remind you, this is the Coulomb's law for pi epsilon 0 Q over R, right? This is the electric field due to Q charge at a distance R in space. Gauss' law, in chapter 21, we have calculated electric field, and in chapter 22, we have calculated electric field, but we have used different formulas and different ways, okay? So now, within this chapter, we would like to get electric potential by using the electric field, okay? So just consider that electric field is given in the question and electric potential is asked, or electric potential is given in the question and then electric field is asked. So with the information which we learned today, you can do that. You can answer such questions. Here, I have a positive charge. And we know that due to the positive charge, we have electric field lines from charge to the space, okay, outward. Electric field lines. And we have electric field tangent to this field lines. And what about the magnitude of electric field here in this point? And what about the magnitude of electric field in this point? We have done it. So the electric field here and the electric field here will be different from each other. We have same Q charge, but due to the distance from the charge, electric field in the points somewhere in the space will be different from each other. Okay, so then if you move outward from charge, the electric field will decrease, right? Magnitude of electric field decrease. Then what about the electric potential? Remember the electric potential formula. Electric potential is given with this expression, 1 over 4 pi epsilon 0 Q over R. Okay? So again here, let's say in A point or in B point in space, you would like to calculate VA or VB. What about their magnitudes? If you're far from the charge, due to this relation, the electric potential will decrease, okay? If you move outward, electric potential will decrease. If you move inward, then electric potential increases, okay, vice versa, due to this relation. It behaves like electric field, as we have discussed just a few minutes ago. Now, the work done by electric force. So in the first part, I have given this expression from physics 1. And you can also use this information for the electric charges, electric forces, okay? So here I have A point, B point, and here we have Q0 charge, and I would like to move this Q0 charge from A point to B point, and during this movement, the force, electric force, does this work, okay? And this work is given with this one, F times dl, and F is electric force, Q0 times E, electric field. And you can also write this one in this form. We have already discussed in the previous transparencies. Okay, then what do you see here? We have work. Just take this work VAB from this equation and rearrange this one, Q0 times VA minus VB. And look at this one. Here we have VAB, same work in different terms, can be written in this form. A, B, Q0, E, DL. Okay, so they must be equal to each other. And on both sides, we have Q0, Q0. Then I can write this expression. We have here VA minus VB. On the right side, we have this integral. Then we have this relation. What do you see here? Electric potential difference between A and B points, VAB, can be written in the form of electric field, in terms of electric field. So finally, I can write this expression between electric field and electric potential. So what was the title? The relation between electric potential and electric field, or finding electric potential from electric field. So then, if you know the electric field, you can calculate the electric potential, or if you know the electric potential, you can calculate electric field, okay? So here we have electric potential on the left side. The unit of electric potential is volt, okay? Just put 1 volt here. And what about the unit of dl? It is meter. Then we can write electric field with the unit of 1 volt per meter. In the previous chapters, we have learned that the electric force is given with this expression. It is Newton, this is Coulomb. Then electric field can be given in the form of Newton per Coulomb. Okay, in questions, you can see Newton per Coulomb or volt per meter. Okay, look at this formula. We have learned a relation between electric potential and electric field, and you think that this is a new information for you. No, it is not. You already know this information, maybe from your high school years. Just remember this discussion from the high school years. Just consider this is positively charged plate, this is negatively charged plate, and there is an electric field from positive to the negative side, uniform electric field between the plates. And let's consider the distance between the plates is D. And what about the voltage difference in between? The voltage difference in between can be written E times D, or electric field in between can be written voltage electric potential per D. Okay, you already know this information from your high school years, and we will repeat them again here, and we will use them to calculate electric potential by using the electric field. Okay, Here we have another term, electron volt. It is widely used in our daily life, electron volt term. So what is electron volt? Just consider that we have an A point here and B point here, and we have a Q charge here. This Q charge moves from B to A. Okay? And potential energy here is UB, and the potential energy here is UA. Okay? And the electric potential here is VB, and electric potential here is VA. So what about the change in the potential energy, delta U? Delta U is given with this expression. UA, final potential energy, and initial potential energy, because this Q charge started to move from B to A, okay? Final minus initial. And in the previous transparencies, we have learned that potential energy can be written with Q times V, or V can be written with U over Q, okay? So remember this formula, just open it like this, then we can have this relation. So what do you see here? If we have an electron, I told you that this is B point, this is the A point, and one charge, Q charge, is moving from B to E, and I have written this expression for that condition. Just consider that this Q charge is electron, and it has E charge. And here we have VB potential, and here we have VA potential. And what about potential difference in between? Just consider that it is 1 volt, okay? Just consider special condition. If the potential difference between A and B points is 1 volt, and if this charge is electron, okay, then the change in the energy, delta U, the change in energy, or final energy minus initial energy, is written with 1 electron volt. This is the charge of the electron. This is the 1 volt, the potential difference in between, 1 electron volt. And of course, the unit of energy is Joule, and the result is also Joule, okay? And 1 electron volt is equal to 1.6 or 2 times 10 to minus 19 Joule, okay? If you know the charge of the electron, you know this is the universal unit of charge. And then you can calculate 1 electron volt. So, and 1 electron volt is equal to this energy. Actually, electron volt is energy, okay? Don't forget. Electron volt is energy. And now just discuss one application of electron volt and energy transfer in cancer radiotherapy. So here you see a device for radiotherapy. You produce high energetic radiations with the energies up to million electron volt, okay? Here we have electron volt, just we have learned, and mega electron volt or million electron volt means that 10 to 6 electron volt, okay? Or 10 to 9 electron volt, this is giga electron volt. So here we have electrons, okay, they are accelerated up to very high energies, okay, from 4 to 20 mega electron volt, so very energetic electrons, and you bombard this body with energetic electrons. So electron comes to the body with huge energies, okay, and then it collides with the tumor cells, okay, and then transfer their energy to the body. Let's consider This is the electron. It has certain energy with MeV, let's say. And here there's a patient, okay? And here, let's say there's a tumor. And then this electron comes here and collides with this tumor cells and transfer this energy to the tumor cell and then heat this tumor cell. And then this tumor cell is destroyed, okay, by energy transfer. Energy is transferred to the heat, okay? So since electrons in this energy up to mega electron volt can penetrate only a few centimeters into a patient, which makes them useful for treating superficial tumors such as those on the skin or lips. What is the meaning of this? This is very nice information. Let me also discuss this one and I will continue. Just consider that this lady or this guy, this patient, has a tumor region, okay, on skin or on her face, somewhere here, okay, just on the surface, okay, and you use energetic electrons. They are accelerated up to these energies and then collides with these tumor cells and then transfer the energy as a heat to the tumor regions and then destroy the cancer cells, tumor cells, okay, on the skin. But what about the inner part of the body? Okay, here you have kidney, heart, and lung, okay? What about the effect of these energetic electrons in the inner organs? Actually, since the electron energies are about MeVs, they can only penetrate a few centimeters, okay? So just consider this is the body of the patient, okay? And this is the skin of the body, just say 1 centimeter. And here we have heart, lung, and kidney, okay? So you send electrons with high energies, but these electrons lose their energies around this 1 centimeter range, 5 centimeter range, and they cannot reach to the inner organs. They cannot be harmful for other parts of the body, and they are only applied to destroy the tumor cells on the skin or lips. I hope it is clear. Electron volt is energy. This is just medical application. Actually, electron volt is used everywhere, okay, in daily life. So we will come to this point later on. Okay, I have 3 examples and then I will finish this lecture. Let me start with example 23.3, electric force and electric potential. So electric force is F, electric potential is volt. A proton with the charge, this one, we have learned this information during the first lecture, moves a distance d 0.5 meter in a straight line between points A and B in a linear accelerator. What is linear accelerator? Linear accelerators are used in the industry, especially to accelerate protons to produce isotopes in cancer therapy, okay? In addition to that, linear accelerators used in scientific investigations. For just consider the CERN, for example. In CERN, protons are accelerated up to very high energies. Of course, in addition to the linear accelerators, circular accelerators of protons and electrons. I will not go into detail, but this is not just an example. This is information from real life, okay? Always keep this information in your mind. So then let me continue to the question. The electric field is uniform along this line. So here we have A point, B point, and we have a proton here, positively charged, you know, positive E, and it is moving from A to B. And the distance between A and B also given 0.5 meter. And there is a uniform electric field in between. Okay, and the magnitude of the electric field is given. Look at the magnitude of the electric field, 1.5 times 10 to 7 volt per meter, or 1.5 10 to 7 Newton per coulomb. Both units of the electric field are used here. I have discussed in the previous transparency. And the direction of the electric field is from A to B. It is given. And then what is the question? Determine the force on the proton. What is the force due to this electric field? And the work done on it by the field, work in order to move this proton from A to B. And the last one, what is the potential difference between A and B? Here we have electric potential VA, here we have electric potential VB, and what is the potential difference in between? Start from the force. Force is given with Q times E. Q is given, E is given. Then I can calculate the force acting on the proton due to the electric field. The second question, what is the work done on the proton? It is given with F times D. We have found the force, put it there. D is given in the question, 0.5 meter. Then you can calculate the work in Joule, okay? Or you can convert this Joule into the electron volt. Here in the previous transparency, look at this information. 1 electron volt is given with 1.6 times 10 to minus 19 joules. So I can convert unit electron volt to the joule. Okay, then I can use this information also here. So instead of joule, I can also calculate work in electron volt, okay, or mega electron volt. So what about the last part, potential difference between A and B points? You can use this expression. Potential difference is given with work over Q. We have calculated work, okay, and you know the Q, then you can calculate megavolt. There is a huge potential difference between A and B points. Actually, in accelerators, it is required. Then let me continue with another question. Example 23.6 from the book, Finding Potential by Integration. So we are looking for the electric potential and we will use the integral. Remember the formula which we have learned in this lecture. By integrating the electric field, find the potential at a distance r from a point charge q. Here I have a positive charge. Since it is positive charge, we have electric field lines outward from charge to the space, okay? Then at certain point here, distance is r, you would like to calculate the potential VA. What is the electric potential at this point? Actually, in the previous lectures, we have calculated electric field in this point, okay, due to this positive charge. Now we will calculate this VA. So here we have this expression, this formula, VA minus VB is equal to minus integral from B to A EDL, okay, just use this expression. And VA minus VB minus EA, don't forget, okay? You see, A minus B, here we have negative sign, B to A, okay? EDL. So, to carry out the integral, we can choose any path we like between points A and B. And here, just choose a point B. Actually, this is the point A. And just set that this point at infinity, B point at infinity. So what about the electric potential at infinity. It is 0. Remember the electric potential energy at infinity. It is 0. And electric potential is also 0 at infinity. Because here I have positive charge and this point is far from this positive charge. There's a huge distance in between. And you know this electric potential energy and those electric potential depends on the distance. If you choose a point at infinity, then both electric potential energy and electric potential are 0 there. So then here I am looking for the electric potential at a point, and this is the B, okay? Then just say that this VA is equal to V, and then here we have this expression from R to infinity. Actually you can also write this one, minus infinity to R, okay? You can also write in this form, don't confuse it, okay? Then just put the electric field here. Just put this electric field and then calculate this integral. You will find the electric potential at a point. This is the result. Now let me finish this lecture with this last example, example 23.7, moving through a potential difference. Here we have a picture. We have 3 nanocoulomb, a positive charge on the left side, and here on the right side we have negative 3 nanocoulomb negative charge, okay? And we have A point here, B point here, and we have a particle in between, okay? And this particle moves from point A to B. What do you see here? In this figure, a dust particle with mass m and charge Q0, 2 nanocoulomb. The charge is 2 nanocoulomb. It is positive charge, and this charge will be repelled by this positive charge and will be attracted by this negative charge. But what about the distance? When the particle is at A, the distance to the positive charge and negative charge are completely different. When it is in the center, there are equal distances to both charges, and when it reaches to B, again, the particle is closer to the negative charge but far from the positive charge. So since the R, the distance between particle and positive and negative charges changes as a function of time, then force is not constant, because force also depends on the distance. Then if force changes, then acceleration changes. Acceleration is not constant, okay, because force is not constant. Then just continue. What is the question? This particle starts from rest and moves in a straight line from point A to point B. What is its speed v at point B? So when it reaches to this B point, what is its speed? Okay, it is asked. So you can use this energy conservation. Remember the energy conservation. K1 plus U1 is equal to K2 plus U2. Instead of 1, you can say A. Instead of 2, you can say B. Okay? Kinetic energy at a point, it starts from rest, then it is 0. And potential energy at a point, Q0 times VA. And final kinetic energy, final potential energy, then you can get this V expression from this formula. And if you calculate the electric potential A point by using this formula, which we have done in the previous transparencies, and if you calculate the potential, electric potential at B point, then you can get VA minus VB, and just take this VA minus VB. We know the mass, we know the Q0, we have calculated VA minus VB, then we can calculate the velocity. This one, I have finished this chapter. In the next lecture, I will continue with the calculating electric potential. Take care of yourself. Bye-bye.